Okay, let's continue. So we'll study operations on points. We have studied how to represent points using coordinates. Now the next natural step would be to consider operations on points. So consider the points in the plane, points in the coordinate plane. Once you fix a pair of x-axis and y-axis, orthogonal x-axis and y-axis, the set of all points in the plane is just the set of all coordinate representations, the set of all x comma y such that x is in R and y is in R. So these are the set of all points in the coordinate plane. Now that we have the coordinate plane, we can ask, can we add points in the plane? So we'll consider the natural definition. Consider points a equals a1 a2 and b equals b1 b2 in the plane. Then we define a plus b to be a1 plus b1 and a2 plus b2. This is how we define sum of 2 points. We just add coordinate wise. So a first coordinate plus the first coordinate of a plus the first coordinate of b will give the first coordinate of a plus b, and so on. A plus b is just a1 plus b1 and comma a2 plus b2, this point. So we can add points this way. Now we can ask, like, what are the properties of addition of points? We have defined this natural addition of points, but does it satisfy nice properties for it to be useful? What are the properties of addition of points? So note that this definition of addition satisfies nice algebraic properties. So for example, commutativity. That is, order doesn't matter. So for any 2 points a and b, a plus b is b plus a. The order in which you add the points doesn't matter. You also have associativity, which is informally grouping doesn't matter. If you have 3 points a, b and c, then if you add a to b plus c, it's the same as adding c to a plus b. So if you are interested in computing the sum a plus b plus c, whether you group b and c together and then add to a, or whether you group a and b together, add them and then add to c, so they give the same result. So grouping doesn't matter. We have commutativity, order doesn't matter. We have associativity, so grouping doesn't matter. And we also have a zero element. So this is a neutral element. So it doesn't change points. So let O denote this 0, 0 point, the origin. then adding O to any point A will not change A. So you have a zero element or a neutral element with respect to this addition of points. And you also have additive inverses. Let A equals A1, A2 be a point. Then there is a unique point. There's a unique point box such that if you add box to A, it gives 0. It gives the origin. 0 here means the origin. Okay. So there's a unique point box such that A plus box is O. This unique point is naturally this unique point is minus A1 comma minus A2. Adding exactly minus A1 comma minus A2 to A1 A2 gives 0. This is the unique point which when added to A1 A2 gives 0. So this is called the additive inverse of A. Okay, so addition of points as defined above, the coordinate wise addition of component wise addition of points or the coordinate wise addition of points. So basically you just add, to add 2 points you just add coordinate wise. This is what the definition says, and so this definition of addition satisfies these nice algebraic properties. We have commutativity, associativity, a zero element, and we have additive inverses for points. Okay, so this is how we can add any two points in the plane. So can we do multiplication? So we can do one form of multiplication, it turns out. So can we multiply points in the plane by scalars? So there are the other forms of multiplication like the dot product and all. We will look at it later. For now, can we multiply points in the plane by scalars? So scalars just mean reals. So let's think about it. Consider a point A equals A1, A2 in the plane, and consider a scalar R, which is a real number. Then the scalar, the R times A, R times this point. Given a point A and a scalar R times this point A is just, again, component wise multiplication by R gives the point R times A. This is how we define a scalar times a point. A real number times a point is just component wise multiplying the components by the real number. Addition of points is also done component wise. So addition, scalar multiplication are done component wise. That's the point. So this is also a natural definition one could consider. Again, what are the properties of scalar multiplication of points? So note that this definition of scalar multiplication satisfies nice algebraic properties. This definition of scalar multiplication satisfies nice algebraic properties. So for example, you have some form of associativity. B times C times A is BC times A. So in some sense grouping doesn't matter. You also have distributivity. So B plus C times a point A is just B times A plus C times A. So these are easy to prove. You just use the definition. So you also have this property, C times A plus B is equal to C times A plus C times B. The proofs are simple. You just take points and just evaluate the left hand side and right hand side and see that they are equal. We can actually mentally see that the left hand side and right hand side are equal. For example, we can think about this equality. So the first coordinate of this left hand side point will be C times A1 plus B1, and the first coordinate of the point on the right will be C times A1 plus C times B1. So naturally C times A1 plus B1 equals C times A1 plus C times B1. So the first coordinates of these 2 points match, and similarly all the coordinates, the rest of the coordinates also match. So even mentally we can see that this equality holds. So you have some form of distributivity and you have a neutral element. So doesn't change points. So it's not really a neutral element in the sense of, so I'll just say a neutral scalar. So there's a neutral scalar 1. If you scalar multiply any point by 1, you will not change the point. And there's also a scalar, let's not give any name to this because there are two basic scalars, 1 and 0. So 1 basically doesn't change the point and 0 basically kills the point. 0 times any point will be 0, will be O. O is the origin, the all zeros point. Okay, so we have these basic properties, these nice algebraic properties for scalar multiplication. So this is how we add and scalar multiply points in the plane. Okay, so that's all for this part. See you in the next part.